You are here. That is what you believe right now. Sitting wherever you are sitting, reading, or listening to these words. You are in a specific place, a specific location in space. Your body occupies a volume. It touches a chair or a floor. It has a definite position in the room. That is what it means to be here. That is what they will tell you. And it sounds right. Of course it does. You can feel the pressure of the surface beneath you. You can reach out and touch the wall. You have an address. A GPS coordinate accurate to within a few meters. Physics itself seems to confirm it. Classical mechanics, the whole Newtonian architecture that put people on the moon, is built on the assumption that objects are somewhere, that particles have positions, that location is a real, definite, measurable fact about the world. That is completely wrong, and I can prove it. See, the idea that you occupy a definite location in space sounds good because it borrows the authority of everyday experience, of classical physics, of every map ever drawn and every address ever written down. But the people who use it, and that includes most of us, most of the time, have made an error. A profound one. They have taken a rule that works beautifully at one scale and assumed it applies everywhere, all the way down, at every level of reality. And when you follow that assumption all the way down to where matter actually lives, where the electrons and quarks that make up every atom in your body actually exist, you find something that should make you stop and look at your hands and feel a kind of quiet vertigo. The real story is much, much stranger than the version you've been sold. When I tell you what's actually going on, what quantum mechanics says is happening to every particle in your body at this exact moment, you're going to realize that the concept of here is not what you thought it was. Not even close. Let me start with why the mistake is so easy to make, because that's actually the interesting part. The reason you believe you're in a definite location is that at the scale you can see and touch and measure with ordinary instruments, position is effectively definite. A baseball is somewhere. A planet is somewhere. A car parked on a street is at a specific address, not smeared across the city in a probabilistic cloud. That's just true. And for most of human history, and for most of engineering and most of astronomy and most of chemistry, that was a perfectly adequate description of reality. Isaac Newton built a complete and breathtakingly successful picture of the universe on exactly this assumption. Objects have positions. Objects have velocities. You know both. You can calculate where anything will be at any future time. The planets, the tides, the trajectory of a cannonball, the orbit of the moon. All of it, derived from the assumption that things are somewhere and moving in a specific direction. This framework was so successful, so precise, so predictive, that by the late 1800s serious physicists were saying, and I mean this almost literally, that physics was essentially done. The big questions had been answered. There were just a few loose ends to tidy up. One of those loose ends was the behavior of light and matter at very small scales. The way hot objects glow. The way electrons behave when you shine light on metal. The way atoms emit very specific colors of light and not others. These were small problems. Footnotes. They figured someone would clean them up with a modest tweak to the existing framework. They were not small problems. They were cracks in the foundation of the entire edifice. And when physicists followed those cracks down, when they took seriously what the mathematics was telling them, they found that the universe at its deepest level does not work the way it looks like it works from where we're standing. Objects do not have definite positions. They don't have definite velocities. They don't have definite anything, not until you actually measure them. And even the act of measurement is stranger than it sounds. Here is where the error creeps in. Most people have heard of the Heisenberg uncertainty principle. It comes up in popular science all the time. And the way it's usually explained goes something like this. There's a fundamental limit to how precisely you can know the position and momentum of a particle at the same time. The more precisely you know where something is, the less precisely you can know how fast it's moving. People hear this and they think, okay, that's a measurement problem. It's an observational limitation. The particle is still somewhere, we just can't know exactly where because the act of measuring it disturbs it. Like trying to find a sleeping cat in a dark room. The cat is in one spot. You just can't check without waking it up and sending it running. That interpretation feels reasonable. It's intuitive. It lets you keep your comfortable picture of the universe, objects in definite places, while acknowledging that our ability to observe those places has limits. It sounds like epistemic humility, like scientific modesty. Pick up a casual description of quantum mechanics. and you'll likely find exactly this framing. People hear uncertainty, and they forget the crucial detail. They drop the word ontological. They keep the word measurement and discard the word reality. Because what quantum mechanics actually says, what the mathematics demands, what decades of increasingly precise experiments have confirmed, is not that the particle is somewhere and we can't know where. It's that the particle genuinely does not have a definite position, not a hidden one we can't access, not one that exists in principle but is concealed from us. The position doesn't exist as a definite value until the moment of measurement creates it. Let me give you a mundane example to show why this distinction matters enormously. Imagine you're baking a cake and you need to know if it's done. You open the oven to check. Now, opening the oven does disturb the cake slightly. The temperature fluctuates, the air moves. But the cake was either done or not done before you opened the door. Your checking didn't change its fundamental state. That would be the classical version of uncertainty, the measurement problem of the sleeping cat. What quantum mechanics is telling you is categorically different. It's saying the cake had no definite doneness before you checked. Not that you didn't know, that it wasn't. The checking, the measurement, the interaction with the system is part of what brings a definite state into existence. And if that sounds like philosophy rather than physics, I understand that reaction. I had it too. But the experiments are unambiguous. The universe at its fundamental level is not made of things with definite properties sitting in definite places, waiting for us to look at them. It's made of something else. Something for which we don't have a good everyday word. Something we describe mathematically as a wave function. The wave function. Let me explain what that actually is, because it's the key to everything we're building toward. A wave function is a mathematical object, a function defined over space, that encodes the probability of finding a particle at any given location if you were to measure it. It's not a wave in any physical medium. It's not a ripple in water or a sound wave moving through air. It's a wave of probability amplitude, and it can be spread out over enormous regions of space. An electron in a hydrogen atom has a wave function, and that wave function isn't a tight little point sitting at a definite distance from the nucleus. It's a smeared-out cloud, a probability distribution that tells you how likely you are to find the electron in any given region if you happen to look. For the lowest energy state of hydrogen, the electron's wave function has its highest value close to the nucleus and tapers off with distance, but it never reaches exactly zero. Anywhere. Not in this room. Not across the city. Not on the other side of the galaxy. The probability of finding it gets absurdly small, staggeringly small. Yes, I mean it. 1 in 10 to the numbers so large they don't have names, but the wave function extends, in principle, across all of space. Think about what kind of object that is. Not a particle sitting somewhere, but a probability cloud stretched across the universe, waiting for an interaction to collapse it into a specific location. And now think about the fact that you are made of approximately 7 times 10 to the 27th atoms. That's 7 followed by 27 zeros. Every one of those atoms contains electrons, each with their own wave function. The nucleus of each atom contains protons and neutrons, each made of quarks with their own quantum states. Every single one of these fundamental constituents of your body is not, at this moment, in a definite location. Each one is described by a wave function, a probability distribution, that in principle extends across all of space. You are not sitting in one place. You are, at the quantum level, a staggeringly complex interference pattern of probability waves, a superposition of quantum states so intricately entangled that it produces, at the macroscopic scale, something that looks and feels and acts like a solid object in a definite location. But that solidity and that definiteness are emergent properties. They're what you get when you zoom out from the quantum world and look at 10 to the 27th particles collectively. They're not fundamental features of the underlying reality. Here is the number that should make you stop and reconsider everything. When physicists calculate the spread, the uncertainty, in the position of a single electron, even in the context of a large molecule in your body, that uncertainty is not a fraction of a nanometer, not something so small it's practically irrelevant. For electrons involved in biological processes, the spread in their quantum wave function is comparable to the size of chemical bonds, the very distances that determine how molecules fold, how enzymes work, how DNA is read and replicated. The quantum fuzziness of your constituent particles isn't some tiny negligible correction. It's operating at the scale of the processes that make you you. Now let me build this up carefully, because this is where it gets genuinely astonishing, and I want you to feel the full weight of it. In the early 1920s, a young physicist named Werner Heisenberg was working on a problem that had been tormenting the physics community for more than a decade. Atoms, when heated or electrically excited, emit light at very specific wavelengths, specific colors, specific frequencies, like a fingerprint. Hydrogen emits red at 656 nanometers, blue-green at 486 nanometers, violet at 434 nanometers. Not a continuous rainbow. Discrete lines. Sharp, specific, reproducible. Niels Bohr had built a model that could predict these lines by assuming electrons orbited the nucleus in specific allowed orbits, like planets around the Sun, and emitted light only when jumping between orbits. It worked. The numbers came out right. The model seemed to explain something profound. But there was a problem. A serious one. Bohr's model required electrons to follow definite paths, definite orbits, with definite positions at every moment. And the more Heisenberg looked at this, the more he realized you could never, even in principle, actually observe an electron doing this. Not because of technological limitations, because of something more fundamental. He sat down, famously, on the island of Helgoland in 1925, recovering from hay fever, and tried to build a theory of atomic structure using only quantities that could actually be measured, actually observed. Not presumed electron positions, but actual spectral frequencies, actual transition probabilities. The mathematics he produced was bizarre. Matrix multiplication, where the order of operations matters, where a times b doesn't equal b times a. And built into that mathematics, unavoidably, was a relationship. The position and momentum of any particle couldn't both be precisely defined simultaneously. Not as a limitation of instruments, as a fact about nature. What Heisenberg had discovered, and what the subsequent development of full quantum mechanics by Schrödinger, Dirac, Born and others would confirm and deepen, is that position and momentum aren't just properties that particles have which we measure imperfectly. They're complementary descriptions, and the universe imposes a strict limit on how well-defined they can simultaneously be. The product of the uncertainty in position times the uncertainty in momentum must always be greater than or equal to h bar divided by 2, where h bar is the reduced Planck constant, about 1.05 times 10 to the minus 34 joule seconds. That's an extraordinarily small number by everyday standards, which is why you don't notice this in daily life. But for particles as light as electrons, it's the dominant feature of their existence. Now let me ask you, does that sound like a measurement problem? Like a limitation of our instruments? Because here is the trick. You can derive the uncertainty principle without any reference to measurement at all. It falls directly out of the mathematics of waves. Any wave, not quantum waves specifically, any wave, has this property. If you want it to have a very well-defined frequency, it has to be spread out in space. If you want it to be tightly localized in space, it has to be made up of a broad range of frequencies. This is just mathematics. It's called the bandwidth theorem in signal processing. Engineers who design radio transmitters and digital communication systems deal with it every day. Quantum mechanics inherits this property because particles are described by wave functions, and wave functions are, well, waves. The universe isn't being coy with us. It isn't hiding information behind a veil of measurement uncertainty. The universe is built from objects that are genuinely, irreducibly wave-like at the fundamental level. And waves don't have definite positions. So how can this be? How can you feel so definitively, so undeniably here if none of your constituent particles are actually anywhere definite? This is where a concept called decoherence enters the picture, and it's one of the most beautiful and underappreciated ideas in modern physics. Physicists call it quantum decoherence, the process by which quantum superpositions become effectively classical, by which the weird wave-like behavior of the quantum world appears from our vantage point, to give way to the familiar, solid, definite reality of the everyday world. Here's what it means in plain language. A single electron, isolated, behaves fully quantum mechanically. Its wave function is spread out. It's in a superposition of positions. It interferes with itself. It tunnels through barriers. It does all the extraordinary things quantum particles do. But you, a collection of 10 to the 27th particles, are constantly interacting with your environment. Every particle in you is bumping into, exchanging photons with, becoming entangled with every particle around you. The air molecules bouncing off your skin, the photons hitting your eyes, the thermal vibrations of the floor beneath you. Each of these interactions is an interaction with something that has its own quantum state. And each interaction entangles your quantum state with the quantum state of the environment. And the environment is mind-bogglingly large, containing unimaginably many particles. The result of all these entanglements is that the quantum superposition of your position, the smeared-out wave function of your center of mass, becomes entangled with an astronomically complex environmental state in a way that makes the different branches of the superposition completely unable to interfere with each other. It is like, and forgive the rough analogy, because this process is genuinely hard to visualize. It is like having two radio stations broadcasting on the same frequency and getting interference, ghostly overlapping signals. Decoherence is what happens when someone tunes those two stations to very slightly different frequencies, so their interference patterns oscillate billions of times per second. The interference doesn't disappear. It's still there in principle, but it oscillates so fast, on such a tiny timescale, that no measurement you could ever perform would detect it. To all practical purposes, and arguably to all actual purposes, it's gone. The quantum coherence of a large object like a human body decoheres, loses its quantum character, appears to become classical, in a timescale that physicists calculate as something on the order of 10 to the minus 40 seconds or less. That's not a short time. That's not even a time in any meaningful operational sense. That's a number so far below any timescale in physics. Far below the Planck time, far below the age of the universe divided by itself a trillion times, that it's effectively instantaneous. The moment a large object begins to form quantum superpositions that could distinguish different classical positions, decoherence destroys those superpositions faster than any process in the universe could detect them. And here is where quantum mechanics whispers something almost too audacious to say out loud. Decoherence explains why large objects appear classical, but it doesn't actually eliminate the quantum superposition. Not fundamentally. In the full mathematical description, in what's called the Everett interpretation, or in the full unitary quantum mechanics without any additional collapse rule. The superposition is still there. It's just entangled with the environment in such a complex way that the different branches can never interfere again. You appear to be in one definite location because all the branches of the wave function in which you're in different locations have become so entangled with different environmental states that they've effectively become separate, non-communicating realities. Whether that means they are separate realities, whether the other branches are real in some sense, is genuinely an open question in the foundations of physics. Not a resolved one, not a settled one. Some of the most careful and serious physicists alive disagree about this. I want to be honest with you about that. But the mathematics is not in dispute. The fact that you are, at the fundamental level, described by a quantum wave function that is spread across space, that is not in dispute. By the way, and I find this extraordinary, this isn't just a claim about human beings, or about life, or about anything special. It's a claim about every object in the universe. The chair you're sitting on, the floor beneath it, the planet under that. Every proton in every iron atom in the Earth's core has a wave function. Every photon streaming from the sun right now is not traveling in a definite direction with a definite polarization. Everything, at the deepest level you can probe, is quantum mechanical. Now let me tell you about a beautiful experiment, because I don't want you to think this is pure abstraction. In 2019, a team of physicists at the University of Vienna conducted an experiment with molecules containing around 2,000 atoms, molecules large enough to see in an electron microscope, and demonstrated quantum interference. They fired these large molecules through a grating and detected interference fringes on a screen, the unmistakable signature of wave-like behavior, of the molecules genuinely existing in a superposition of paths rather than taking one definite path. Objects you could, with great effort, see, behaving like waves, taking multiple paths simultaneously. That experiment didn't create quantum weirdness. It revealed it. The quantum weirdness was always there, in every object, at every moment. The experiment just created conditions quiet enough, isolated enough from environmental decoherence, to make it visible. And larger experiments are being planned. There is currently a research program, led by groups in Vienna, Delft, and at MIT, aimed at demonstrating quantum superposition in objects approaching the scale of a living cell. A living cell. The technical challenges are formidable. You need to isolate the object from its thermal environment, cool it to near absolute zero, prevent any photon or air molecule from carrying away information about its position. But the physics says it should work. The physics says even a living cell should, under the right conditions, behave like a quantum wave. There is one more piece of this story, and it is the piece that tends to make people very quiet when they hear it. The quantum nature of your constituent particles isn't just a philosophical curiosity. It's not just a statement about your fundamental ontology that has no bearing on your actual biology. The quantum wave-like nature of particles in your body is functional. It does things. It is part of why you work. Enzymes. The molecular machines that catalyze every chemical reaction in your biology, that digest your food, replicate your DNA, generate your energy, work partly through quantum tunneling. A proton or a hydrogen atom, instead of going over an energy barrier the way a classical ball would roll over a hill, passes through it. Not around, not over, through. Because its wave function has a non-zero amplitude on the other side of the barrier, even when classical physics says it can't get there. Calculations suggest that some of these tunneling events occur at rates thousands of times faster than they would if the particles were classical. Your enzymes are quantum devices. Photosynthesis, the process by which plants and certain bacteria convert sunlight into chemical energy, the process that feeds nearly all life on Earth, involves quantum coherence in a direct and measurable way. When a photon is absorbed by a light harvesting complex in a leaf, the energy doesn't travel through the molecular network by classical random hopping from one molecule to the next, the way a person might wander through a maze. It spreads as a quantum wave, exploring multiple pathways simultaneously, and the quantum interference between those pathways helps direct the energy toward the reaction center with extraordinary efficiency. Around 95% of absorbed photons result in a stored chemical reaction. 95%. Classical random hopping would give you something far less impressive. The leaf exploits quantum mechanics to harvest light with a precision that still makes engineers stare. Your eyes, the photoreceptors that allow you to see these words, detect single photons. One photon, the minimum possible unit of light. And the detection mechanism involves a quantum process. A single photon isomerizes a single retinal molecule, flipping it from one shape to another, triggering a cascade that becomes a nerve signal. Your vision operates at the quantum limit. So now let me circle back to where we began. You are here. That's what you believed. And I want to be precise about what was wrong with that and what was right. It was right in the sense that decoherence is real and powerful. At the macroscopic scale, at the scale of bodies and chairs and rooms, the quantum wave function of your center of mass is so thoroughly entangled with the environment that all quantum superpositions of your gross position are effectively, and for all practical purposes, eliminated. You are in one room, not in a superposition of rooms. The GPS coordinate is real and meaningful and useful. But it was wrong in the sense that this classical definiteness is derived, not fundamental. It's what falls out of the quantum mechanics when you average over the environment. The bedrock isn't classical. The bedrock is a wave function. Every atom in you is described by quantum mechanics. Every electron in you is delocalized over its orbital, genuinely spread in space, not hidden somewhere definite. And those electrons are not irrelevant bystanders. They are the chemistry. They are the bonds. They are the biology. They are you, in the most fundamental sense. You are a quantum mechanical object that has learned, through decoherence, to behave classically at large scales. But the quantum reality doesn't go away. It's still there, operating, doing work, making you function at every moment. When you look at your hands, you are looking at something that your physics tells you is, at the deepest level, a superposition of states, a wave function, a probability distribution. The sensation of solidity, the resistance you feel when you press your palms together, is electromagnetism. It's the electromagnetic repulsion between the electrons in your hand's atoms and the electrons in the other hand's atoms, a quantum force operating between objects with wave function descriptions, generating the classical sensation of contact. You never actually touch anything, in the sense of two solid objects making contact. The electrons repel before any classical contact can be made. Same quantum mechanics, same wave functions, same decoherence. At the level of atoms, at the level of molecules, at the level of you. And here is what I find magnificent about this. Not just intellectually, but in a way that feels almost moral. We started with the question of where you are. And the answer quantum mechanics gives is, you are spread, not localized. Your constituent particles are probability waves, entangled with the environment, doing quantum calculations in your enzymes and your photoreceptors and your neural synapses. While the collective behavior of 10 to the 27th of these quantum objects produces, at the scale you can see and feel, something that looks for all the world like a solid person sitting in a definite place. You are not simply here. You are a quantum process that locally, contingently, for the purposes of every macroscopic interaction, acts as though it is here. And there is something almost elegant in that. Not dispiriting, not disturbing, elegant. The universe managed to build objects that experience themselves as definite, as localized, as here, out of ingredients that are fundamentally indefinite, delocalized, quantum mechanical. The next time someone tells you that you are in a definite location, I want you to ask them one question. At what scale? Because the answer depends entirely on what scale you're asking. At the scale of rooms and cities, yes. At the scale of molecules and electrons, not at all. The world is not what it looks like. It never has been. The table you might be resting your arm on right now is mostly empty space. Its apparent solidity the result of quantum electromagnetic forces. You yourself are a standing quantum wave in a bath of environmental decoherence, classical at large scales, irreducibly quantum at small ones, and the transition between those two descriptions is one of the deepest and least fully understood problems in all of physics. We started with the belief that you are here, definite, located, solid, in a place. We discovered that this is an emergent, approximate, scale-dependent description of a fundamentally quantum mechanical reality in which position is not a pre-existing property, but something that arises through interaction, through measurement, through the entanglement of wave functions with the vast quantum environment that surrounds and permeates and constitutes everything. That does not make the experience of being here less real. It makes it more extraordinary. You are not a billiard ball sitting on a pool table in a definite spot. You are a quantum mechanical process, ancient and elaborate, shaped by 13.8 billion years of physics, running on quantum tunneling and electromagnetic repulsion and decoherence and probability, managing at every moment to produce the experience of a conscious being in a definite location, reading or listening to these words, thinking about what they mean. That is what you are, right now. The uncertainty in your position is not a failure of physics to describe you correctly. It is physics describing you correctly, and the description is staggeringly more beautiful than the simple story we tell ourselves when we say I am here. I think you'll agree that the truth is far more astonishing than the version you've been sold. And here is the question I want to leave you with, the one I genuinely want you to think about, and, if you feel moved to, answer. If the definiteness of your location is an emergent property rather than a fundamental one, if here is something that arises from quantum mechanics rather than being written into the bedrock of reality, then what does that say about the definiteness of you? Is the self, the sense of being a particular person in a particular place at a particular time, also an emergent property, also approximate, also scale-dependent? And does that idea disturb you? Or does it thrill you to know that even your sense of being here is one of the universe's most elegant quantum accidents?